In this video, we're going to talk about the definition of continuity. So we say that a function f of x is continuous at a if the limit as x approaches a of f of x equals f of a. So in other words, the limit of f of x as x approaches a needs to exist, and moreover, what that limit is needs to be equal to f of a, whatever the y value of the function is when we plug a in for the x. And if we break this down a little bit more, what does it take for the limit as x approaches a, this is a two-sided limit, to exist? Well, for the two-sided limit to exist, we know that the limit as x approaches a from the left, that's what the minus sign indicates, of f of x, it needs to be equal to the limit as x approaches a from the right, that's what the plus sign indicates. Those need to be equal, and they need to be finite. And for it to be continuous, those need to be equal to f of a. So in general, for a function to be continuous, there's two ways we can sort of state that. The first way is how the definition says it, where it says, the two-sided limit of f of x as x approaches a is equal to f of a. Or the other equivalent way is to say the limit as x approaches a from the left of our function equals the limit as x approaches a from the right of our function, and both of those equal f of a. All right, so let's look at an example. All right, so in this example, I'm going to use a graph that we saw in the videos, in one of the videos from the previous section, 3.1. Okay, so I have this graph, and what I want to do now is I want to determine if my function f is continuous or discontinuous, and discontinuous just means not continuous, at the following points. Okay, so there is a very conceptual way to think about whether a function is continuous or discontinuous, and I'll mention what that is after we work this problem out, just using the definition, because I want to make sure that the definition makes sense and we're able to apply it. Okay, so I have these 5 points here, these 5 values of x. In fact, let me scooch these down a little bit to give myself a little bit more room here. Let's shift it one more down, line down. Okay. So what I need to do for all of these is I need to determine, well, what's the limit? Let me write it a little bit higher, actually. What is the limit as x approaches a, whatever point we're testing, from the left? What's the limit as x approaches a from the right? What is f of a? And once I know those 3 things, I will know whether it's continuous or not continuous. So once I know those, I will know whether it's continuous or not continuous. Okay, so I'm going to make a table here basically to sort of organize my work, just because I have so many points to test that making a table, I think, will be helpful. Okay, so let's separate these out into some rows. Some rows. Okay, here we go. Oh, okay, I need one more horizontal one to separate those labels at the top. Okay, so now let's start thinking about these limits and what f of a is for these points. Okay, so let's do part A first. For x equals 1. So what's the limit as x approaches 1 from the left? So here's where 1 is. And as we approach 1 from the left, that's this part of the graph. I'm sort of tracing out here. The y values seem to get really close to this point's y value, which is 4. What about as x approaches a from the right-hand side? As we approach a from the right-hand side, in this case it's 1, as we approach 1 from the right-hand side, that's this part of the graph. And those y values seem to get close to the y value of this whole, which is 2. Okay, at this point we can actually tell whether it's continuous or not continuous without even figuring out what f of a is. It doesn't even matter. The fact that, let me just recap a little bit. For my function to be continuous, all 3 of these need to be the same. Because these 2 are already different, we know our function is discontinuous. It is discontinuous at x equals 1. Just for practice though, what is f of 1? The closed circle at that point has a y value of 4. And that's what it would be. Although we technically didn't even need that to answer this. All right, so let's continue to -3. I'm going to start to pick up the speed here a little bit with these. Okay, so -3, as we approach that from the left, that is this part of the graph. Those y values seem to be getting close to the y value of the whole, which is 1. Okay, remember, what's happening exactly at that point, at -3, which is up here, that does not matter for the limit. Okay, because the limit, we just care about what's happening as x gets close to -3, but not equal to it. Okay, so the limit as we approach it from the right is the same. It's also, so it's this part of the graph as we approach it from the right. And the y values there are getting close to the y value of the whole, which is 1. So far so good. So far it matches up with it, might be continuous. But what's f of -3 when you plug -3 in? When you plug a -3 in, you get this point up here. That's where the closed circle is. The y value is 5. Okay, so the f of -3 is 5. So all 3 of these are not the same. Only 2 of them were the same. So it's not continuous. It is discontinuous. Okay. What about as x is, when x is -4? So -4 is here. So the y value there is 0. So let's fill out f of -4, that's 0. And looking at it, the limit as you approach -4 from the left and from the right are both also going to be 0. So from the left is, sorry, not 1, it's 0. That's what the y values are getting close to. And same from the right, the y values are getting close to 0. So it is continuous. That's the first one we had so far out of this list where it was continuous, because all 3 of them are the same. What about as x approaches 3? So from the left-hand side, as you approach 3, this is where, that's this part of the graph here, trending downwards. That limit is -infinity. And now what about as you approach 3 from the right? Technically, though, we actually don't even need to know that. We actually don't even need to know the limit from the right or f of a, because when we say that all 3 of these have to be the same, they all have to be some finite number. At this point, it doesn't even matter what these other 2 are. We can say that it's discontinuous. But the mere fact that this first one was -infinity, that's kind of nice. We save some work there. Okay, what about for x equals 5? For x equals 5, how about this time we'll do the limit from the right. So the limit as we approach 5 from the right, so that is this part of the graph. X is getting closer and closer to 5 from the right-hand side. The y values there are also trending down towards negative infinitely, sort of infinite number, so that's -infinity. And that's enough at this point to say that these 3 things could not be the same finite number. So it is discontinuous. All right, and that answers our question. So I do want to make a brief comment about this. There's a conceptual way to tell if something is continuous at a point or not. And the conceptual way is, so I'll add that comment here, conceptually, a function is continuous if we can draw the graph through whatever point that we're talking about, specifically through that point, x equals a, without lifting our pencil. And looking at this picture, if we think about some of these numbers, like x equals 1. At x equals 1, if we try to draw the graph there, we reach this closed circle, but then we have to sort of jump down and lift up our pencil to continue the graph. Because we couldn't draw the graph without lifting our pencil, that's why it's discontinuous there. We can make a similar argument for a bunch of these, or for all of them, in fact. Like at -3, when we draw it on one side of -3, I have to lift my pencil to now go to the other side of the hole. That matches this sort of conceptual definition. So I want you to understand this, both conceptually, this without lifting the pencil way, and also this technical way in terms of limits and what f of a is, and all three of these need to be the same because that's the original definition, and I want that to make sense. Okay, so just for practice, I'm going to fill out the rest of this table. So, because I also want to do it to answer another follow-up question right after this, which is, well, let's fill out the table first. So as x approaches 3 from the right, what is that limit? So that would be this part of the graph trending up towards this vertical asymptote. So that is getting infinitely large, so this is positive infinity. There is no point on the graph, no closed circle there, where x is 3, which means f of a is undefined. F of 3 is undefined. What about when x equals 5? What's the limit as we approach 5 from the left? So as we approach 5 from the left, that is this part of the graph that's trending down. Okay, so that limit would be negative infinity. And what about f of 5? What's the value of the function at 5? Well, there's no closed circle there, so that is also undefined. Okay, so now that I have this completely filled out, I want to ask a follow-up question about limits. At which of these values, which of these values does the limit as x approaches a of f of x not exist? Okay, so let's think about that. So for x equals 1, well, so for the limit to exist, we need these one-sided limits to be the same. In fact, let's write that down. For the limit as x approaches a of f of x to exist, we need the limit as x approaches a from the left of f of x to be equal to the limit as x approaches a from the right of f of x, and both must be finite. Both must be finite. Okay, so for x equals 1, the one-sided limits are different. One of them's 4 and one of them's 2, which means one of the answers to this is x equals 1. It doesn't exist. The limit does not exist because the one-sided limits are different. Okay. In fact, let's write that down as the reason. One-sided limits are different. That was the reason why there. What about at negative 3? At negative 3, the one-sided limits are the same and they're both finite. So at negative 3, it does exist. Same thing at negative 4. The one-sided limits are both the same. They're both 0, which is a finite number. So negative 4 does exist. What about at x equals 3? At x equals 3, there's actually 2 reasons why the limit doesn't exist. One is there's infinite stuff going on. One's infinity, one's negative infinity. The other reason they don't exist is they're different. So when x equals 3, the limit doesn't exist. 2 reasons. One-sided limits are different. And the second reason is, and they're infinite. And they are infinite. Okay, and then finally at x equals 5, they're the same, but they're infinite. And that's infinite falls into the D and E category. So x equals 5. The one-sided limits. Actually, if even one of the one-sided limits is infinite, the whole thing does not exist. One-sided limits are infinite. But recall that when we have a scenario, in this case, the limit as x approaches 5 of f of x, even though this falls into the D and E category, it's one of those instances where I can be more specific because it's the same from both sides. So I would write negative infinity as opposed to D and E because this is more specific. Okay, but to answer this second question, these are the values where the limit does not exist. It's 1, it's 3, and it's 5. So in terms of our goals, we have defined what it means for a function to be continuous at a point